more galvanic cells and overall reactions and cell reduction potentials. But today what we're going to do is we're going to put all that together by using the notation for a galvanic cell, okay? Now, this actually comes from example 9.5, but what we're going to do is we're going to talk about what this notation means as we go through the problem, okay? We can see all of these different types of chemical elements in here, and we can see straight lines, we can see double straight lines. What does all that stand for, okay? Well, when we have a galvanic cell, the way that this is worded, or the way that this is set up, is that the electrode always comes first, and for the other side, it comes last. And this double line in the middle tells us that this is where the salt bridge is, okay? So this is one side, this is the other side. If you have just one straight line, that tells you that there is a phase change. Now, an electrode is always going to be solid. And so this, as you can see on this side, since it's telling me it's molar, and that means this is going to be aqueous solution. On this side, once again, here I have, these are all aqueous solutions because it's telling me the concentration. Here's another phase change. And then the electrode is going to be solid, okay? Now, what comes on the left-hand side is going to be the anode. And if you recall, the anode is the place where the oxidation takes place because you have two vowels. Then on the right side is the cathode. And that's where reduction takes place because you have two consonants there, okay? Now, armed with that information, I should be able to figure out what my two half reactions are, what the overall reaction is, what the cell potential is. I can diagram everything out, okay? So let's take it one piece at a time. Let's start with what is going to happen here. Now, on this side, I only have iron and an iron ion. And I know that oxidation has to take place. And so if oxidation is going to take place, that means that this is going to have to be Fe going to Fe2 plus 2 electrons. That makes sense, right? Because oxidation means that I'm losing electrons, and here that's exactly what I've done. I've lost electrons, okay? And if I look at the table in the back, I can see that the standard reduction for this half reaction is 0.440 volts. Just like that. Now, this kind of looks like a mess. It's not so easy to tell what's going on over here. And so in this case, you can actually look at the table to help you out. Remember that the electrode is not always involved in the half reaction. It is sometimes, but it doesn't have to be. And so if you look through the reactions that are in that table, you will find a reaction that has MnO4 minus, and you'll find one that has hydrogen ions in it, and you'll find one that has Mn2 plus in it. That's the only one like that in the whole table. And so we know that in order for this to happen, we have to be, since this is reduction and we're gaining electrons, we know the electrons are going to have to go on the left-hand side. So if I just look at the table, that's going to give me this particular reaction. MnO4 minus plus AH plus 5 electrons goes to Mn2 plus 4 H2O. And you're probably going, okay, I see this, I see the hydrogen, I understand the electrons, I see that one, where's the water? Well, in the description for this, he does tell you that we're not going to use water. We don't have to put that in there because the water doesn't really, water can be present in the reaction without having to be listed up here because it's water, okay? And therefore, I can also get from the table that this, for this half reaction, I'm going to have 1.51 volts. Okay? So, for the cell, the standard reduction for the cell is 0.440 volts plus 1.51 volts, which is going to give me 1.95 volts for the cell. Okay? Then I need to figure out the overall reaction for the cell. Well, I've lost 2 electrons, but I've gained 5. And obviously that's not going to work. It's got to be the same on both sides. So I'm going to take this reaction and I'm going to multiply it by 5. I'm going to take this reaction and I'm going to multiply it by 2 in order to get my overall reaction for the cell. And again, what I'm going to do is, as I write this, I know that the electrons are going to drop out because I've got 10 on the right and I've got 10 on the left, so I know they're going to drop out. So I'm not going to bother to write it and cross it out and rewrite it again. I'm going to save myself some time and some effort and some pencil lead. And so as I go to write this out, I'm going to have 5 FEs on the left side. On the left side over here, I have 2 MnO4 minus plus 16H plus goes to, I have 5 Fe2 plus on the right side over here, and on the right side over here, I'm going to have 2 Mn2 plus 8 H2Os. Okay, so now let's double check everything. 5 irons, 5 irons. 2 manganese, 2 manganese. 8 oxygens, 2 times 4 is 8. I have 8 oxygens here, 16 hydrogens here, 16 hydrogens here. Okay, so the atoms are balanced. How about the charge? Well, I have a positive 16 and a negative 2, which makes a positive 14 on this side. On this side, I have 2 times 5 is a positive 10, and 2 times 2 is a positive 4, which makes a positive 14 on that side. So both atoms and charge are balanced, so I'm good there, okay? The other thing that's left now is to draw the cell. And again, this is another reason why I told you earlier, I like to always put my anode on the left, because when I draw it from notation like this, I can go from left to right like I did before anyway. So I think I'm going to try to, let's draw a box here. I'm going to put the drawing in here. And so I've got my 2 containers, and I'm going to have my 2 electrodes. I know that on this side, this electrode is an iron electrode, and I know that I have iron electron, or I have, yeah, iron ions in here, and that is connected on this side to a platinum electrode, and I know that I have to have a salt bridge, because that's a part of any galvanic cell. I'm going to have MnO4 minus in solution. I'm going to have Mn2 plus in solution. I'm going to have H plus in solution. And then my electron flow is going to go this way. In my salt bridge, my negative charges are going to go this way, and my positive charges are going to go that way. There's the salt bridge. And then I can label my anode and my cathode. So as you can see then, if I do it in the same order that this is written in, it does make it much simpler, okay? So what is going on now as this reaction proceeds? Well, as the reaction proceeds, the iron electrode is going to get smaller, while the iron ion concentration is going to get bigger. And on this side, the concentrations of the MnO4 and the hydrogen ion are going to go down, while the concentration of the Mn2 plus is going to go up. Okay, and we're not really going to see anything happen to the platinum there. It's just a method, a way for it to get the electrons from one side to the other. Okay, so there we have summarized that with the notation from a galvanic cell.